You open your electricity bill. You go through the line items. There's your energy charge, kilowatt hours. You understand that one. There's your demand charge, kilowatts. You're wrapping your mind around that one too. And then there's this other line. It might say power factor adjustment. It might say excess kVA charge. It might say reactive energy, kVAR. Or you might not see it as a separate line at all. You might just notice that your billed demand is significantly higher than the metered demand printed on the same bill, and you have no idea why those numbers could be different. If you manage a manufacturing plant, a chemical facility, a cold storage operation, or any industrial facility with significant inductive loads, and you've ever looked at that section of your bill and thought, I don't really know exactly what this is, but it's really costly, well, this episode is for you. Today, we're decoding power factor penalties and power factor correction strategies. So here's the direct answer before we go deeper. Power factor is the ratio of what's called real power. It's the kilowatts and kilowatt hours your equipment actually uses to do work, to apparent power, which is the total power your utility has to supply you to keep that equipment running. Now, stick with me here because those things will become crystal clear. When that ratio of real power to apparent power falls below the threshold written into your tariff, your utility charges you for the difference. The good news is that power factor correction is one of the most effective and most proven cost reduction strategies available to a commercial or industrial facility when it's designed correctly based on your actual tariff and your actual power quality data. I'm Daniel Burke, and this is Energy Answers by Tactical Energy Group. This episode is for plant managers, facility managers, maintenance directors, COOs, and anyone responsible for the electricity costs at a manufacturing plant, a chemical facility, a cold storage operation, or a large industrial facility. In other words, if your operation runs motors, transformers, HVAC compressors, or any other significant inductive load, and virtually every one of those operations does, then power factor is going to be relevant to your bill. Whether your utility penalizes you for it, how heavily, and what to do about it is exactly what we are going to cover today. So the core decision question for this episode is, how can you effectively identify, calculate, and implement power factor correction strategies to eliminate utility penalties and optimize electricity costs in your facility? So let me start with what power factor actually is, because this is one of those concepts where the technical explanation is real, but the translation for a facility operator needs to be clear before anything else will make any kind of sense. Okay, power factor is the ratio of real power to apparent power in your electrical system. Real power, measured in kilowatts, is the power that actually performs work. It spins your motors, it heats your elements, it drives your processes. Apparent power, on the other hand, is measured in kilovolt amps, or kVA. It's the total power your utility has to supply to keep that equipment running. When real power and apparent power are equal, your power factor is 1 or 100%, and that is the ideal. In almost every commercial and industrial facility, they are unequal, and that gap creates the financial problem. The reason they're not equal is a third kind of power. It's called reactive power. Now, reactive power is measured in kVAR, kVAR, or kilovolt amps reactive. It does not perform work in the conventional sense. It doesn't spin a shaft or move a load. What it does is establish and maintain the magnetic fields inside the inductive equipment, motors, transformers, HVAC compressors, without which those devices cannot function at all. In a previous episode, we used the 12-passenger van to explain load factor, with kilowatt hours as the riders and demand as the size of the van. Now, in that same frame, reactive power is the fuel inside the tank, inside the van. It doesn't carry the passengers, but without it, the van does not move and no passengers go anywhere. Reactive power is the enabling environment within which real work is done. So the relationship between real power, Reactive power and apparent power is visualized in electrical engineering as a right triangle. It's the power triangle. Real power forms the base. Reactive power forms the vertical side, and apparent power is the hypotenuse. It's the longest side, the total. The angle between real and apparent power defines your power factor. When there's no reactive power, the vertical side is 0. The triangle collapses to a flat line, and your power factor is 1. As reactive power grows, that vertical side gets taller, the angle increases, apparent power exceeds real power, and your power factor drops below 1. Now, for commercial and industrial facilities, the power factor is almost always what's called lagging, meaning the current waveform lags behind the voltage waveform. And this is a direct result of inductive loads. It's not something operators are doing wrong, it's a function of the type of equipment industrial facilities run. And that is exactly why most commercial and industrial operators have never thought to manage it, because nothing about daily operations feels different when power factor is poor or when it's good. The problem shows up strictly on the bill. So let me cover how utilities penalize for low power factor, because the mechanisms vary by utility and by rate, and understanding your specific tariff is the only way to know what your facility is actually dealing with. The first penalty mechanism is a direct surcharge on reactive energy. Some utilities meter reactive energy in kilovolt amp reactive hours, or kVAR, kVARh, and bill for it directly when it exceeds a certain percentage of kilowatt hour consumption. You'll see this as a line item on the bill. Most operators have no idea what it means. The second mechanism, and in my experience, one of the most common in Indiana commercial and industrial rate structures, is an adjustment to your billed demand based on your actual power factor. The formula works like this. If your tariff requires a minimum power factor of, let's say, 90%, and your actual power factor is 80%. Your billed demand is calculated as your metered kilowatts, you're divided by your actual power factor. So if your meter reads 1,000 kilowatts, a megawatt, and your power factor is 80 or 0.8, your billed demand becomes 1,250 kilowatts. You're paying for 250 kilowatts of demand that your meter never actually registered. That is the power factor penalty. It's not labeled clearly. It simply shows up as billed demand that's higher than metered demand, and most operators never have been told why. The third mechanism is demand billing based on kVA rather than kW. Some utilities base their demand charges on apparent power, not real power. If your demand is billed on kVA and your power factor is poor, your kVA demand is always higher than your kW demand for the same real load. Every demand charge you pay is inflated accordingly. Now, the fourth is a power factor clause, a tariff provision that adds a direct percentage surcharge to your bill for every percentage point your power factor falls below the tariff threshold. A common structure is 1% added to the bill for every percent decrease in power factor below 95%. Now, that's not the hard and fast rule, but that's an example of how this can be set up. If your power factor runs at 75%, that's a 20% addition to your entire bill. That's super painful and very costly. So all four of these mechanisms have something in common. None of them announce themselves clearly. They're written into the tariff in language most operators will not recognize as a penalty. You'll not know how to calculate it, and you'll not think to challenge. The utility has your meter data. They know what your power factor is, and I'll come back to this when I give you my honest take. They have essentially no structural incentive to help you understand and correct it. In what world are you incentivized to help your customers pay you less? It's just not how the system works. Now let me talk about what you actually gain when you correct power factor, because the benefits extend well beyond just the bill. The most immediate benefit is eliminating the penalty. Whatever mechanism your tariff uses, kVAR, surcharges, demand, inflation, a power factor clause, correcting your power factor to the threshold eliminates that cost. For a manufacturing facility with a significant power factor problem, that is commonly tens of thousands of dollars per year at minimum, and usually much, much more. The case study in our source material, a manufacturing plant correcting from 82% to 97% power factor, eliminated penalties, and entirely reduced kVA demand charges sufficiently to save $45,000 each and every year. The project paid for itself in under 24 months. Now, the second benefit is increased electrical system capacity. You see, when you correct power factor, you reduce the reactive current flowing through your distribution infrastructure. That frees up capacity in your transformers, your switchgear, your subpanels, and your distribution system. A 1000 kVA transformer serving an 800 kW load at 80% power factor is fully loaded. It has nothing left. The same transformer, though, serving an 800 kW load at 95% power factor, is operating at about 840 kVA, leaving meaningful spare capacity. And you always want some reserve margin in your transformer. You can expand production, add equipment, bring on new processes without upgrading the transformer. Now, low power factor effectively derates your existing infrastructure. Correcting it expands the usable capacity of equipment you already own. Third benefit is reduced heat losses in your conductors and equipment, what electrical engineers call resistive losses, which means wasted energy you're currently paying for that produces no output. Higher current flowing through conductors generates heat. That heat is waste, energy you're paying for that produces nothing. A 25% increase in current from poor power factor results in more than a 50% increase in those heat losses. Correcting power factor reduces the current, reduces the heat, and improves the efficiency of every conductor and connection in the distribution system. The fourth benefit is extended equipment lifespan. Excessive current and the voltage stress associated with poor power factor accelerates wear on motors, transformers, and controls. Equipment modeled to last 15 years may fail at 10. And here's what I want to say directly to the plant managers and COOs listening. That accelerated wear is nearly impossible to track back to a power quality problem. You replace a contactor and assume it's just normal wear. The capital outlay across your operation accelerates year over year, and no one connects it to a power factor number on a utility bill. So I'll say more on this when I give you my take a little later. Now let me walk you through the types of power factor correction equipment, because selecting the wrong type is where projects could go sideways. The primary correction method is a capacitor bank. Capacitors generate reactive power locally inside your facility. So your equipment gets the reactive power it needs without drawing it from the utility transformer. The fundamental principle is local reactive power supply. You produce it on your own premises rather than importing it from the grid. Fixed capacitors produce a constant amount of reactive compensation. They're appropriate for loads that are stable and predictable, a large motor that runs continuously at a consistent load. They are the simplest, lowest cost option when the load profile does not fluctuate significantly. Automatic power factor correction banks, or APFC banks, use a relay controller to switch multiple capacitor steps in and out based on real-time power factor readings. When load increases and power factor drops, the relay brings on more capacitance. When the load drops, steps are switched out. This is the right solution for facilities with variable loads, operations that start and stop, processes that cycle, shift schedules, and create significant swings in demand and power factor throughout the day. Detuned filter banks add inductors in series with capacitors. They're the appropriate solution for facilities with significant harmonic distortion, which I'm about to address directly because this is where correction projects can fail when the design is not properly done. Active harmonic filters are the most sophisticated solution. They inject opposing harmonic currents while simultaneously providing reactive power compensation. They're super cool. They are appropriate for facilities with high and severe harmonic distortion, high concentrations of variable frequency drives, UPS systems, and other non-linear loads. On placement, correction equipment can be installed individually at each major inductive load, in groups at the feeder level, or centralized at the main service entrance. The optimal approach depends on your facility layout, the concentration of inductive loads, and the scale of the problem. In many facilities, a combination of individual correction on the largest motors combined with a centralized APFC bank at the service entrance is most effective. Now, let me address something that absolutely cannot be skipped and that too many power factor correction projects do. Before any capacitor bank is installed in a commercial or industrial facility, a harmonic analysis must be conducted, and here's why. If your facility has significant nonlinear loads, variable frequency drives on motors, LED drivers with electronic ballasts, UPS systems, switching power supplies, your electrical system almost certainly has harmonic distortion. Harmonics are voltage and current distortions at frequencies above the fundamental 60 hertz. They're a byproduct of how nonlinear loads draw current. Standard capacitors do not cause harmonics, but when standard capacitors are installed in an environment with existing harmonic distortion, a resonance condition can develop. The capacitors interact with the system impedance at a harmonic frequency and amplify the distortion, sometimes dramatically. This can damage your equipment. It can trip breakers and cause the power quality problems you are trying to solve to become materially worse. The solution for harmonically distorted environments is detuned filter banks, not standard capacitors. This is not an optional upgrade. It's the difference between a correction project that functions correctly and one that introduces new problems into your electrical system, and you don't want new problems. Any vendor or electrical contractor who proposes a capacitor bank without including harmonic analysis as part of the assessment process has not designed a solution for your specific facility. They've designed a solution for a hypothetical facility, and that distinction will show up in the results. Now we'll talk about the overcorrection risk, because this one catches people off guard. The goal of power factor correction is not a power factor of 100%. Overcorrecting, installing more capacitance than the load requires, can cause what's called leading power factor. This means the current waveform is now ahead of the voltage waveform. Lagging was behind, leading is ahead. Some utilities penalize leading power factor the same way they penalize lagging. And in facilities where production loads drop significantly, a weekend shutdown, a seasonal slowdown, a temporary line curtailment, overcorrection against a light load can cause voltage rise conditions and trigger penalties, even when the facility is not producing at all. I've been in a facility that had to shut down its production lines while its power factor correction equipment kept running at full capacity. The overcorrection against essentially no inductive load created very significant penalty conditions. The facility was paying for a new problem it had created while trying to solve an old one. The target for most commercial and industrial facilities is a power factor between 95 and 98% lagging. That range eliminates penalties, it avoids overcorrection, and accounts for normal load variability. APFC banks are specifically designed to stay within that range dynamically. This is not a detail to delegate entirely to a vendor. This is a parameter you need to confirm your correction system is designed and controlled to maintain across your actual range of operating conditions. So let me walk you through what a correct power factor correction implementation looks like, because the process matters as much as the equipment. As always, the first step is reviewing your utility bill and your tariff language. Before you engage a contractor, before you request a quote, you need to know whether your specific rate on your specific utility includes power factor language. What's the threshold? How is the penalty calculated? Is demand billed on kW or kVA? This is a tariff review. Open the rate book and find the relevant provisions, or work with someone who can do that work for you. Now, at this point, the second step is a comprehensive power quality study. On-site measurement of your actual power factor parameters across a representative operating period. Real power, reactive power, apparent power, power factor, and harmonic content. not a 7-day temporary logger, even though that's industry standard. You need revenue grade and power quality grade monitoring that captures the full range of your operational conditions, including startup events, shift variations, and any processes that create variable loads. Harmonic analysis is part of this step. It's not optional. It's the prerequisite that determines which type of correction equipment is actually appropriate for your facility. The third step is calculating the required kVAR for correction. Based on your current power factor, your target power factor, and your real power load, an electrical engineer calculates the specific amount of reactive power compensation needed. This calculation must be based on your data. It has to be based on your data. Now, the fourth step is selecting and sizing the equipment based on that calculation with appropriate safety margins and capacity for future load growth. The fifth step then is installation by qualified commercial electrical contractors with post-installation verification, actual measurement of power factor after commissioning to confirm the system is performing as designed. And the sixth step, this is the one most facilities execute very poorly, is ongoing monitoring and maintenance. This brings me to the most dangerous and least discussed failure mode in power factor correction. And I want to be direct about this because I have seen it firsthand in several facilities. The equipment's installed, it commissions correctly, power factor improves, it's all doing its job. Penalties come off the bill, and then at some point, months later, maybe a year or two later, a breaker trips or someone manually switches the capacitor bank off for some reason and nobody turns it back on. The power factor penalties come back. The equipment is sitting in the electrical room or by the switchgear, wherever it is, completely functional and completely off, and nobody knows. In one version of this, the utility bills are on auto pay. The finance team processes them without reviewing the line items. The people managing the facility operations and the people handling the utility invoices are in entirely different departments with no regular communication about what's on the bill. Power factor penalties accrue for months. No one connects them to the capacitor bank that has been switched off. This is not a hypothetical scenario. I've seen this several times. We've also seen this equivalent with solar installations. Maybe you've heard some stories. A large, expensive system is installed and sitting completely off because it was never properly commissioned or a disconnect was never reconnected. The assumption is that because the equipment is installed, it's performing, and that assumption is costly. Now, the practical implication, if you have power factor correction equipment, you need live monitoring on your power factor, not a monthly bill review, not periodic inspections, but live monitoring, so that if the equipment goes offline for any reason, you know immediately, not 30 days later when the penalty has already appeared on your bill and you're on the line to pay it. And if your facility's utility bills are on auto pay, take them off autopay. Make sure your finance team goes through a basic training on how to read utility bills. This is the most straightforward, lowest cost step any large organization can take right now to stop paying for problems they cannot see and have never been trained to find. And if you want to set up a training like that, I wasn't expecting to do this, just reach out to me. I will show your team how to audit their own utility bills. It's super important. It can save you a lot of money. Let me connect this back to something we covered in this series in a previous episode, because power factor creates a specific version of a problem that we have already discussed. When a utility bases demand charges on apparent power, kVA, rather than real power, something specific happens to your all-in cost per kilowatt hour. Your billed demand is higher than your metered demand. The demand charges you pay are calculated against a number that exceeds what your equipment actually drew. When you take your total bill, including those inflated demand charges, and divide it by the kilowatt hours you actually consumed, your all-in cost per kilowatt hour is higher than it would be if billed demand accurately reflected real power, or kW, instead of kVA. This is a load factor problem. Listen up, it's a load factor problem caused by a power factor penalty. And load factor and power factor are different. Go back and look at the previous episodes. A poor metered load factor means your demand is high relative to your kilowatt hour consumption. A poor power factor that inflates billed demand above metered demand means your billed load factor is even worse than your metered load factor. You're paying for capacity you never used, not because of how you operate, but because of a billing provision you may not even know exists on your tariff. Now, I'm going to take a second and address something I said. There is typically no metered versus billed load factor line item on a commercial or industrial bill. But load factor is something we deduce from billed and metered metrics on the bill, and load factor is the key metric. When I say billed load factor versus metered load factor, I'm talking about the relationship between kilowatt hours consumed to potential kilowatt hours as determined by your peak demand in the billing cycle. If that peak demand is determined by a runaway kVA because of a poor power factor, now we have a situation where we have an oddly high billed load factor. Getting back to it, correcting power factor does not save kilowatt hours in a material sense. The financial benefit is the elimination of penalties and the reduction of kVA demand charges. But when those charges come down, your all-in cost per kilowatt hour does improve because the total bill decreases against the same number of units consumed. Now, there's one more dimension I want to address because it rarely comes up in these conversations, and the consequences of ignoring it are real. Transformer health. Your facility's electrical infrastructure, the transformer stepping voltage down to the level your equipment uses, has a kVA rating. A kVA rating. That represents the maximum apparent power the transformer can continuously deliver. When your power factor is poor, the kVA demand on that transformer is higher than your real kW load might suggest. A transformer that appears to have spare capacity based on kW demand may be close to fully loaded or excessively loaded based on kVA. And a transformer that's consistently loaded beyond its rating runs hot. Heat accelerates insulation degradation. A transformer designed to last 25 to 30 years fails at 12 to 15, and no one knows why. When it fails, the operational disruption is severe. Production stops. Lead times for replacement can run weeks and months at times. And emergency replacement costs are multiples of what planned maintenance could have and would have cost. Here's what I've observed across hundreds of facilities. Utilities have a surprising lack of awareness about the actual loading conditions of their secondary transformation assets. They don't track what load is connected behind most of their meters, and in my experience, they operate with something close to a run-to-fail posture on their secondary transformers. That means the transformers they put on your location. They don't proactively manage transformer loading, they don't monitor for overload conditions, and they will not intervene until equipment has already failed and cost you dearly. So if your facility is on a secondary service, meaning the utility owns the transformer, the burden of knowing whether that transformer is appropriately sized, whether it's being properly loaded, and whether power quality issues are accelerating its degradation falls on you. The utility is not managing it. I can promise you that, so the customer has to. Now let me give you my honest take, what we've all been waiting for, because there's something very important here that goes well beyond the technical explanation. Power factor correction is, in my assessment, one of the most effective and most underutilized cost reduction strategies in commercial and industrial energy management. And the reason it's underutilized is not because it doesn't work, but it's because it has no marketing. It's not part of the energy transition narrative. It doesn't come with government rebate programs or national press coverage or a sales ecosystem built around making it accessible or attractive. If you want solar, there are dozens of installers and multiple incentive programs and a constant stream of marketing telling you to act. If you want LED retrofits, it's the same story. Power factor correction, though, an electrical contractor or an energy consultant tells you, usually in technical language, and you find it difficult to evaluate, and Unfortunately, the conversation typically ends there. But I want to tell you something about why utilities have not made power factor correction a part of their efficiency rebate programs. It's because I've had this conversation directly with someone inside an Indiana utility who designs energy efficiency programs, and I personally recommended that power factor correction be added to their efficiency rebate structure. Now, the person I spoke with personally agreed that it was warranted and beneficial, and they said the utility would never go for it. And here's what I believe is behind that. Utilities in Indiana and broadly have a cost recovery mechanism that allows them to recoup revenue lost when customers become more efficient. It's crazy. When a customer uses rebate dollars to install LEDs and consumes fewer kilowatt hours because of it, the utility calculates that lost kilowatt hour sales revenue across the entire customer base and includes it in the next rate increase cycle. Every dollar of efficiency the customer achieves is eventually recovered by the utility through higher rates that everyone pays later. Power factor penalties are different. They're not lost kilowatt hour sales. They're lost penalty revenue. And the mechanism for recovering lost penalty revenue in a rate case before a regulator is different from recovering lost kilowatt hour sales, and from what I can observe, far less straightforward to justify. My honest assessment is that power factor penalty revenue is lucrative. The cost recovery pathway for lost penalty revenue is complicated or non-existent, and utilities have no structural incentive to help their customers eliminate it. Their behavior is fully consistent with that assessment. So here's what this means for you. No one is coming to help you identify a power factor problem. Not the utility, not a rebate program. It will fall to you, or to a qualified energy partner who knows how to read your tariff and compare it to your data. And if a commercial electrical contractor or a qualified energy consultant tells you that you have a power factor problem and recommends correction, I would take that recommendation seriously. This is not a product category with aggressive marketing or widespread vendor malfeasance. It's a technical observation that's almost certainly simply true. When someone is recommending you correct power factor, there's essentially no hype ecosystem pushing them to say it for any reason other than that you have a power factor problem. Now, with that said, the framework never changes. Verify that your tariff has power factor language. Confirm that your billing data shows a penalty or an inflated billed demand. Require that the correction system be designed using your actual power quality data with harmonic analysis included. Require that the system be modeled against your specific rate to show you the before and after on your all-in cost per kilowatt hour. Your tariff, your data, your rate calculator, your bill, model it, verify it, implement it. Let me bring this all together. Power factor is the ratio of real power to apparent power in your electrical system. When it drops below the threshold in your tariff, your utility penalizes you through demand inflation, kVAR surcharges, kVA-based billing, or power factor clauses. Those penalties are persistent, often invisible, and in most cases, completely avoidable. Correcting your power factor eliminates those penalties. It reduces kVA demand charges, frees up capacity in your existing electrical infrastructure, reduces heat losses, and extends equipment life. The return on investment for well-designed correction projects is typically 1, 2, or 3 years. The project must be based on your actual power quality data. A harmonic analysis is not optional. It determines which type of correction equipment your facility actually needs. The target is 95 to 98% lagging power factor, not 100%. The system must be properly sized for your load profile, and after installation, live monitoring is the only way to know immediately if the equipment goes offline and penalties begin accruing again. Now look, I know I don't run your plant. That's your job. My real job is to translate this billing complexity and give you the questions and the leverage you're not getting from someone's sales presentation or from the rate book or from utility customer service. The bottom line on power factor penalties and correction strategies is this. If your utility rate includes a power factor clause, excess kVA charges or kVAR billing and your facility runs significant inductive loads, you're almost certainly paying a penalty you could eliminate. And the correction strategy is well proven, not technically complex at the operator level, and typically pays for itself within 2 to 3 years when it's designed using your actual tariff and your real data. So here are 4 questions to take into a morning huddle or your next meeting with finance, operations, or your facilities team in the next week. Question 1, does our current utility rate, our specific utility provider, does it include a power factor clause, a excess kVA demand charge, or reactive energy billing in kVAR? And do we know the threshold at which a penalty is triggered? You have to know that question. You have to know the answer to it. Question 2, when we compare our billed demand to our metered demand on our last 12 months of utility bills, are those 2 numbers consistently different? And if so, has anyone determined whether that gap originates from a power factor provision in our tariff rather than from perhaps demand ratchet, which you can learn more about in a previous episode? Question number 3, if power factor correction equipment, capacitor banks, APFC panels is already installed at this facility, do we know with certainty that it is currently online and operating? Or is there a possibility that a tripped breaker or a manual shutdown has rendered it inactive while penalties continue to accrue? Question number 4, if a vendor or electrical contractor is proposing power factor correction, can they show us using our actual power quality data, our actual harmonic content analysis, and a functional equivalent of our specific utility rate, what our billed demand and all-in cost per kilowatt hour will look like before and after the correction? I know it seems aggressive, but this is a bar that any vendor worth their salt could willingly and easily clear. So before I close, I'm going to speak directly to 2 groups of listeners. If today's episode was useful and you're not currently facing an active power factor project, the most valuable thing you can do with what you just learned is send it to another operator. Send this episode to another operator, a facility manager in your network who's dealing with the same questions about a bill that keeps going up and nobody has explained why just yet. But if you're in a second group, if you're in an Indiana commercial or industrial environment with a serious electric bill and you're actively trying to determine whether your facility has a power factor problem, or if you've been told that you have one and you're trying to evaluate whether and how to act, I want to talk to you about the Energy Decision Blueprint. Here's what it looks like. We start with a brief discovery call to confirm that your tariff has power factor language and that your billing data shows a real opportunity worth going deeper. From there, we pull your last 12 months of bills and relevant operational context. Then I'll sit down with you, and when it's appropriate, I'll bring in one of our rate experts, and we'll run your actual data through the same rate engine I use for existing TEG customers. We show you what your bill is actually doing around power factor today. We model what correcting it would realistically do for your bill and your all-in cost per kilowatt hour on your specific tariff. That's the most important part. And we produce a simple board-ready 1 or 2 page summary. The current situation, the realistic savings range, and whether I see a real economic play and under what conditions. For qualified accounts, this Energy Decision Blueprint is free. And there are 2 outcomes and only 2. If there's a real play, I'll show you exactly what it looks like. If there's not, if your rate does not penalize power factor or your power factor is already within an adequate range or the correction cost does not justify the savings on your specific account, I'll tell you that straight to your face so you can stop spending time and organizational energy pursuing something that will not actually improve your costs at all. If you want that for your power factor situation, go to blueprint. Thanks for listening to Energy Answers by Tactical Energy Group. If this helped, send it to another operator who's dealing with the same headaches and visit tacticalenergygroup.com to get more practical tools for your facilities.